Hi guys, welcome to the 8.2 video, Slippery Slopes. Okay, so we're just going to kind of work this through together, just for timing's sake. Yeah, here we go. While working on Is It Right in the previous module, you looked at several examples that lead to the conclusion that the slopes of perpendicular lines have negative reciprocals. Your work here is to formalize this work into a proof. Let's start by thinking about two perpendicular lines that intersect at an origin like these. Okay, so we got these two perpendicular lines. We're going to kind of finalize what we've been talking about before about negative reciprocals. Okay, or opposite reciprocals, as you probably heard me call them. Start by drawing a right triangle with the segment OA as the hypotenuse, and these are often called slope triangles. Based on the slope triangle that you have drawn, what is the slope of the line OA? Okay, so we know how to do this. Slope OA. We want to use a triangle, and this is just a visual triangle, not quite the same triangle of 8.1. My goodness. This would be a run of 3, a rise of 2, so we would say that the slope would be 2/3. Cool. Now rotate the point 90 degrees about the origin using the coordinates of the image OA. Or what are the coordinates of the image of point A? Okay, so we rotate it 90 degrees. We're actually going to rotate it 90 degrees counterclockwise. So we're going to head that way. Luckily, they've drawn these perpendicular lines for us, and we know these perpendicular lines have a 90-degree angle in between them, so our point A ends up being here. We don't really want to say it's A, though, right? We kind of want to call it something that's like, this was A, but it's not anymore. Many of you probably recall prime notation. So we'll go ahead and use prime notation. Sweet. Now, what are the coordinates at that point? That would be back 2, up 3, -2, 3. Sweet. Moving right along. Using this new point A prime, draw a slope with the hypotenuse 0 or OA prime. Base the slope of the triangle. What is the slope of OA prime? So what is the slope of this new one now? Here's the same O. We want to know this line. What's the slope there? Drawing a new triangle, it's now back 2 and up 3. And so we would say that the slope is -2/3. Oh, I'm sorry. No, it's back 2 and up 3, pardon me. I did run over rise. That would be back up 3 and back 2, so -3/2. Now you're like, why'd she put the negative on top, right? No, remember negatives can float wherever they want. It's kind of ugly to have it in the denominator. Don't know why, but it is. So we kind of just put it on the outside. Alright, cool. What is the relationship between these two slopes? How do you know? Ooh, hey, kind of the point of the task, right? We've done this before. -3/2, +2/3. Yeah, I would argue that those are negative versions of each other, and I would argue that those are reciprocals of each other, and so we could argue parallel. I'm sorry, perpendicular. Sorry, I got too excited about the next thing. Perpendicular lines. You may or may not have seen me use this symbol before. It means perpendicular. It's not a plus sign, right? It's just an upside down T. But it's perpendicular lines, and I'm lazy, so I don't write that. I don't write perpendicular the whole thing. Alright, cool. I hope that was kind of like basically a warm-up task. We kind of talked about this, but if not, no big deal. Is the relationship change if the two lines are translated so that the intersection is at -5, 7? What do you guys think? Probably not, right? It doesn't really matter that this is the origin, because that same thing, you're going to get the same slope. That is what's great about linear lines, is that their slopes are constant. They are the same no matter where we are. We're talking exponential, yeah, we got a different situation. It's curving, it's flying all over the place, right? But this is still happening. This cross, this perfect T is happening no matter where it's placed, right? And those slopes are going to be the same. And so those slopes are still going to be opposite reciprocal. So no, they will not change. And we could say something along the lines of linears are constant slope. We cannot say that for any other type of curve, because then any other type of curve is not a line. Alright, cool. So now that was a very specific example, right? It was very kind of concrete, like here's one. Let's see if we can broaden it to sort of no matter what. To prove a theorem, we need to demonstrate the property holds for any pair of perpendicular lines, not just a specific example. It is often done by drawing a very similar picture to the example we've just tried, but using variables instead of numbers. Using variables to represent the idea that it doesn't matter, Using variable represents the idea that it doesn't matter which numbers we use, the relationship still stays the same. Let's try this strategy with the theory about perpendicular lines and have slopes that are negative reciprocals. Alright, so same idea, but now there isn't an O and an A, and it's clearly negative 2/3 or negative 3/2 and positive 2/3. It's going to be more variably. You're going to see this a lot in college, which is really fun. Alright, we have the information that lines L and M are constructed to be perpendicular. Talked about constructions recently, so we know they are perpendicular. Start by labeling a point P on line L. Why not there? We could put it on the bottom, who cares? Label the coordinates of P. Ooh, interesting. I'm going to call this P1 and P2. I can't guess what they are. That's the whole point of this. I want to use variables. You could call them A and B if you wanted to. I'm going to go with P1 and P2. Draw the slope of the triangle from point P. The slope of the triangle from point P, we're going to say to their intersection, like the same way we did last time. So we'll call this O, because why not? And then, there is the triangle. I can't tell you that that's run of 2, rise of 5. I can tell you, though, it's a run of P1 and a rise of P2. Cool beans. Label the sides of the triangle with the slopes using variables like A and B for the rise and run. Okay, we went with P1 and P2. Like I said, you could call them A and B. It's all good. All right, number 6. What is the slope of line L? Now that we've done this picture in variable form, it's the same picture as before, right? It's the same exact picture. A little less lopsided, right? It's kind of more of a higher rise. But we can do the same thing. The slope now would be rise over run. Do I know P2? Do I know P1? No. Doesn't mean I can't plug them in. It's basically the slope formula, right? It's the slope formula. Ooh. But we want to make this more... Dang it. Alright, now you may be arguing, well, didn't we just talk about it not being at 0, right? So shouldn't we do something like P2 minus O2 over P1 minus O1, which would be more of my slope formula? Yes, I 100% agree with you. We could do that. But seeing as how it doesn't matter where it starts, we can kind of force it to start at 0. Okay, so I'm just going to call P2 the difference between the intersection point and the point of this, the y of this point. Okay, so I'm just going to call it that. If you want to talk a little bit more about that, we can. But for now, P2 over P1 is good. Alrighty, moving right along. Rotate point P 90 degrees about the origin, label it P prime, and mark it on line M. What are the coordinates of P prime? Okay, once again, we'll just go whoop, and luckily we have these already defined, perpendicular lines. And so we'll call this P prime. What are the coordinates of said P prime? Well, if this was P1, if this was P1, P2, well then I'm going to have back P2 and up P1. So this is going to be the coordinate negative P2, comma P1, right? And we learned that back when we were doing rotations. If you forgot, rotations, flip it around, we switch and we negate, right? And so we get this 90 degrees. All right, cool. So the coordinates would be, lost my notes, negative P2, P1. And again, if you're using A and B, that's fine. You can just use A and B, negative B and A. I like P's because then it tells me it's about the point. All right, cool. Draw the slope of the triangle from point P prime. What are the lengths of the sides? How do you know? Well, I found them the way that we just found the point. So I go back P2, I go up P1. Otherwise, I'm not going to get from 0, 0 to this point. So you could say, you know, rise over run, distance formula, however you want. So we drew those lengths in as we worked. What is the slope of line M now? So we can use this information to now find the slope of line M. It's going to be rise, careful now, P1 over negative P2, aka negative P1 over P2. Cool. What is the relationship of the slope between these lines? Check it out. Negative P1 over P2 versus P2 over P1. Yeah, I would say those are negative, and I would say those are reciprocals. So I would say they're perpendicular. say they're negative reciprocals. And so we've pretty much just proved they have perpendicular lines have this relationship. Is the relationship between slope change, is the relationship between the slope change if the intersection of M is moved to another location? How do you know? No, it's not, right? It's not going to be any difference. The same argument as with actual numbers. We move it around, we can just call P2 the difference in the numbers instead of just P2, right? Instead of just a point, we can say P2 is Y2 minus Y1. And again, we come back to that slope formula argument. So they would not be different. No. And then I'm just going to write answers may vary. You can explain that in any way you want. Is the relationship between slopes changed if L is rotated to M? Oh, if L and M are rotated. So if everything was rotated, if we had a slightly different picture, no, it would not be different because the rotation rules are the same. You rotate by changing the point that way, and so you're going to get the changed slope that way as well. So no, because rotation rules are constant, oh goodness, are always the same, or however you want to word that. Since we did use things like variables, right, instead of actual numbers, it doesn't matter what those numbers were. And so if we rotated this picture in any way, all that would do is change the sizes of P2 and P1. And so, yeah, it would be the same thing. We'd still just call them P2 and P1, though. It wouldn't change anything. All right, cool. So, how do these steps demonstrate the slope of parallel lines or negative reciprocals for any pair of perpendicular lines? I'm actually going to let you answer that one because it's a very open-ended question about how do these demonstrate. It's kind of like, why does this proof prove this? But it's something along the lines of, it doesn't matter where you are, you can rotate it, you can translate it, you can move any of these perpendicular lines around, but that same relationship will apply. So I'm going to let you go ahead and answer that. Alright, that was a lot of information, that was a big old proof with a lot of variables, but if you see the relationship between the two, should be okay. Okay, next up, now think about parallel lines like the ones below. Parallel lines, woo! Okay, what do we know about parallel lines? We know their slopes are the same. They are the same, right? No matter where they are increasing at the same speed. So we're going to now do the same idea. We're going to prove that kind of, first we'll do an example, then we'll go do it with variables. Alright, cool. So we have this point here, 0C and AB. Draw the slope from point A to the origin. What is the slope? Draw that same triangle guy. And it looks like, since it's the origin, we know this is 0, 0. We get A, and down here, B. And so the slope would be rise over run. A over B. Beautiful. Okay, transformation. What transformation maps the slope from horizontal line OA to the other line M? What transformation would map this slope? See. Well, it'd be a shift of some kind. Yeah? Translation, probably, is what we call those shifts. And I would say it's a vertical one. Right? Vertical, up and down, not side to side. And so we'd say it would be a vertical translation of distance. How much? How much did it go up? Ooh, it doesn't actually say, but if we were to say it in terms of variables, I would say it was a translation, vertical translation of C. Because we can see it went from 0, 0 to 0C. It went up about C much. Ha, sounds funny. Went up about C, right? So it went up about C. What must be true about... There is a missing page here. That's annoying. Anyway, what must be true about the slope of line L? Why? What must be true here? It has to be the same. It has to be the same because we just took one line and moved it up. If you remember back to translations, translations would just be something like f of x equals g of x plus, in this case, c. We didn't change g of x. We didn't change f of x. We didn't change m. We didn't change l. We just moved it. And so their slopes have to be the same. Alright, cool. The last one of this is basically doing the same thing with M and L not having any points on it. So I'm going to let you figure that out. I'm missing the page here, but it's basically the same writing. So it's just kind of like an open-ended, you draw the same picture, it's basically this. These are examples of proofs. Proofs have to be variables. You can't just sit there and list off every number and make sure it works for everything. So that's kind of where variables really come into play. You can make lots of claims about lots of numbers with variables. All right. Have any questions? Let me know.